So I have the Ferris wheel. Ha ha ha. Ferris, ferric. Sisters. Because it's cis, right? Same side versus the trans formation. Transistors. Come on, people. I'm trying here. Cis and trans. You know what I'm talking about?
Yes. No, I don't get the gender.
Because they're trans, they're opposite on opposite sides, so it's trans sisters because they're sisters on different sides.
Oh.
Versus on the same side.
I thought it had to do something with the names.
No, nothing with the names. Polymer, many mers, right? Mer. Paradise, and Paradise lost because they lost their dice. Okay, I got two more. You're not part of the solution, you're part of the precipitate. We know that though. And then my absolute favorite. What is this? Okay, so say no. Okay, so I was gonna say thank you for wearing, sporting that jacket today. I appreciate that. Okay, so you guys have your notes from yesterday. Have them on your desk. Have your after reading on your desk. Somebody give me their definition of oxidation. You took an 11-minute video. You want 11-minute video. Is that too dark on that side room? My board is dying, so just forgive me. Give me your definition, Allie, of oxidation reduction.
Good morning, students and staff. Excellent job on the drill today. You guys did an awesome job. Students who have signed up for the PSAT with last names A through L, please report to the cafeteria this time, unless you are in band. If you're in band, you will come during fourth period. Again, students who sign up for the PSAT, last names A through L, please report to the cafeteria this time. Thank you and have a great day.
All right, my people who are leaving, there's a video happening right now, so you're going to watch the video sometime for yourself, and just that'll give you some heads up on what we're doing. Okay, so Allie, back to you, girl.
Losing an electron because it's transferring to another
element. Okay, so losing electrons, oxidation, right? Somebody tell me what reduction is then. Yeah, gaining electron. What was the little acronym at the end of the video that would help you determine how that definition is done? Oil, rig, or Leo says, Bye, people. Bye. Okay. Otherwise, everybody's with me. Okay. If you need to sit up here so that you're not facing, or sit on that side so you're not facing the back, whatever. You know. Okay. So oil rig. So what we're going to be talking about today is just transfer electrons. Have we ever transferred electrons before? All the time, right? And what kind of compounds? Definitely ions, right? So that's like the definition of ionic bond. Transfer electrons. That's why ions have a true oxidation state. So the oxidation state, which you saw in the video, was like a little chart, like an imaginary chart we place on top, where we assign an element, yes? So, sodium's in group 1, it's a metal. Chlorine's in group 7, it's an elemental. Chlorine will always lose one electron. Its ion charge is +1, and its oxidation state is +1. And then chlorine gains electrons, so its charge is a -1. Isn't that? Thank you. Bye. Somebody run me in 5, okay? So anyway, if you have an ion, you definitely have an ion charge. That is also your oxidation state. However, carbon dioxide, what kind of bond is that for? Covalent. Does it have an ionic charge? Do covalent things have ionic charges? No. But sometimes we have to track electrons. Where do they go in a reaction? So what we do is we assign something that's covalent down. We still assign it oxidation states, meaning fake charges, basically is all they are. We still assign them because we need to track where electrons are going. Because in order for us to follow the law of conservation of mass, right, law of conservation of mass, we know that electrons essentially are massless, but when I say essentially, that still means they have they're 1/2000th of the mass of a proton. They're still really, really tiny, but they still have mass. So we still have to make sure we know that whatever electrons were lost in the reactants were gained in the products or vice versa. We still have to track them. So that's us tracking them with fake charges. Sometimes the charges are truly, the oxidation states are truly the charge. Sometimes the oxidation state is just an assignment that we give to it based on its electronegativity differences. So that's kind of what this whole idea is. Generally, a lot of people lump this with Unit 2 because it's just reactions. It's just another type of reaction. Actually, it's the same. It's every type of reaction. Almost every single reaction is a redox reaction. Synthesis, decomp, combustion, single replacement. Double replacement is the only type of reaction that's not truly redox. Every reaction does have electrons being transferred in some way or form. So that's why it's relevant, and it still plays into Unit 2 stuff. Got me? Okay, so towards the end of this unit, we're going to be doing a real-life application kind of project related to oxidation reduction. So as you're going through this unit, start to think about where does this play out in the real world. But we are all going to be theming it towards our oceans, global chemistry crisis, beach trip thing. Okay, so that's what we're theming it towards, so that we have some continual progress on that. And that's where you're going to start a little bit today on that. So you watched your video on this. I'm expecting you know some of this. Also, you took your active reading guide, which has the oxidation states that were assigned. You guys have that out? Have your active reading guide out so that you can tell me what oxidation states are assigned. I'm going to walk through a couple of just recap notes, and then we're going to move to there, okay? So we really briefly talked about writing oxidation numbers or oxidation states. And we talked about how they are really truly ionic charges if it's an ionic compound. But in molecular compounds, it's just how we denote where the electrons are. So molecular is the same thing as saying what? Not ionic, covalent, okay? So the oxidation number, the oxidation state is used to just represent where the electrons exist if it were to give up its electrons, like through an ionic bond. And so these are some examples. A lot of our transition metals have many oxidation states they can take on, or oxidation numbers they can take on. For example, manganese can take on different charges, which we have here as +2, +3, +4, +5, +6, and 7. That's because, look at manganese. You guys have the periodic table in front of you, right? Look at manganese. What's its electron configuration? Do you guys remember electron configuration? So, like, take magnesium back to its last noble gas, which would be argon. Okay, and then finish up. What is that? 4s, 4s2, 3d, 5. Okay, so technically, it truly has. So the fourth is the fourth energy level. That's the valence electron shell. Truly it has 2 valence electrons. But because 4s and 3d are very similar in their energy states, truly it has the ability to lose all 2 + 5, so 7 valence electrons. You can see it happening. When it loses 2, this manganese actually forms a pinkish color. When it loses 3 electrons, it forms this is actually like a whitish lime, and then 4, 5, 6, and 7, you can see that the color changes with it as the oxidation state, or quote-unquote charge, changes as well. So a lot of these are transition metals, and all these transition metal oxidation states have a different color associated with them, and that's how we get this plethora of colors that we can use in like art and paint, but also we see in solutions. So copper 2 will always form more color. Blue. Copper 1 is actually green. You notice copper 1 is not on here, but there is such thing as copper 3, which we never see. But it's an oxidation state, not truly a charge like copper 1 and copper 2 are. So oxidation states and charges are very similar, but not the same thing. That's the goal of this. Okay, so you guys took down these rules in your active reading guide, yes? Rules. These rules are rules to be followed whenever you're applying oxidations or assigning oxidation numbers to a compound. So one thing for sure you should absolutely always remember is that if you have a free element or a diatomic, you will give it the oxidation state of 0. It does not have to share electrons with anybody, or if it is a diatomic, you'll be sharing the electrons very similarly. So that's why neither of them get a plus or minus. They get a 0. If you have an ion, the ion has already either given up its electrons or taken electrons. Its charge is its oxidation state. There is no question about that. Its charge is its oxidation state. If you have a particle that's a polyatomic ion has numerous atoms involved, and its charge of the polyatomic ion it should be equal to all the oxidation states added together. So the sum, and I think examples mean more to you than these rules right now, but these examples will kind of use these rules as we go, so we're going to them first. So the sum of the net charge of a compound is just a compound and not an ion. The compound's net charge will always be 0. But if it's a polyatomic ion, the polyatomic ion's charge will equal the sum of all the oxidation states. So those are the general rules, and I think they make sense because they correlate to some of our ionic charges. But when we're looking at compounds and we're like, oh, I've got a covalent compound, what do I prioritize in terms of assigning oxidation numbers? The things you always prioritize are, if you have a metal involved, the metal gets its charge based on its ionic charge. So metals are really easy. Like it's not a secret. We know group 1 always gets a +1 charge. We know group 2 always gets a +2 charge. So that's not a secret. We know that. Hydrogen generally, is it electronegative? Does hydrogen want its electron? No, it's like, take it, I'm free to be just a proton, hence why we call hydrogen proton. It will always form a +1 oxidation state. And the weird way that it's really minute, it's a minute difference between a charge and oxidation state. You'll notice that I'm trying my best to keep it like this. 1+ is oxidation state, +1 is a charge. Hear that difference? It's minimal. So if it's written as a 1 and then the sign, it's considered an oxidation state. But if it's a plus and then a 1, it's the ionic charge. It's really easy to mess that up, and it's totally fine if you do. I just want to make sure that you know that's why I'm doing that. Thank you. Fluorine will always get a -1 oxidation state. Why does that make sense? Why would fluorine gain? You done?
No, I wasn't even supposed to take it.
So on the list.
Yeah, no,
That's why I was
sorry.
so
I don't
confused.
remember actually signing.
Okay,
So
jump in with us, jump in. Okay, so why does fluorine get a -1 oxidation state? If there was a struggle between it and something else, like electronegativity. Yeah. It's the most electronegative on the entire periodic table. No one will ever win against fluorine. It will always get the electron, hence why it gets a -1 oxidation state. Oxygen's very similar. Oxygen's very electronegative. It will always get a -2 in terms of its oxidation state, unless it's compared to fluorine. Fluorine wins. That's why this is a priority listing here. Fluorine will always win. So if you give OF 2 or something like that, we will give fluorine its -1. Let me do that example down here a little lower with more space. Fluorine will get an oxidation state of a -1 or 1 negative. So if I have to have this whole entire compound overall equal to 0 for its oxidation states, -1 times 2 is what? -2. So oxygen has to balance that by getting a +2. So I have +2 and then 2 -1s here, and that overall gives us a net of 0. That's what I mean by compounds equaling 0. And their oxidation states, generally we write them on the top of the numbers just like this to assign them, but they sum to what the compound should be, which was net 0. We're going to use some examples with that. So along the rules of exceptions, while I'm going over a couple, you can see them over here. Hydrides, which is where you have the H as an anion. H is on the back side, not the front side. It always gets a -1 as its oxidation state, or a 1-. You can see I'm already messing that up. -1, 1-, but it doesn't matter. Peroxides, because it has 2 oxygens and a 2 negative charge, you can do the math. If I have 2 oxygens and there's an overall -2 charge, then you can tell that each of those oxygens should have a -1 as its oxidation state, because they net to 2-. And then superoxides, we rarely will ever be exposed to those, but they actually have a non-integer, full integer oxidation state, but generally we won't see that too often. Okay, let's apply these rules. And this is what I want you guys to do. Work through 1 or 2 with me, and then I want you to try a couple yourself. I'm going to put the lights back on because I got some sleepy people. Sleepy. Okay. I'll give you that. All right, so let's do sulfur trioxide first. Prioritize. Who do I give an oxidation state to first? Sulfur or oxygen? Oxygen, because it's on my list of priorities, right? So I'm going to put a negative, or 2- or -2 up here. So -2 is oxidation state of oxygen. Total oxygen with its 3 here means I have a net of what on this side? -6 or 6 negative, right? So oxidation states for the whole compound has to equal 0. So if this over here is a -6, what does sulfur have to do to balance? Be a 6+ or a +6. Okay, oxidation state of sulfur is +6, oxygen is a -2. That's how you assign them. It's just math. It's just algebra. Let's do another one. Let's do C. What is the name of this, by the way? Hypochlorite. Okay, who do you prioritize? Sodium's a group 1 metal, right? What does it always get? Okay, oxidation state of 1 plus. Okay, who's our next priority? Oxygen, so we're going to give it a 2 minus. Okay, so far 1 plus, 2 minus. So what does chlorine have to do to balance that? It does have to be 1 plus. So this basically is like an algebra problem. I'm going to try to make it like that. 1 plus x and a minus 2 equals 0. X has to be a plus 1. Okay, so I can keep explaining it through algebra, or you can balance it in your head. It's just they basically need to sum to 0. Okay, keep going. Let's do I down here. What would you consider that? Anybody? 0. It's a free element. It's not bound to another type of atom. It's a free element or a diatomic element. It's not fighting for its electron. Either it's sharing equally, or it's just got it itself. So this is an allotrope of sulfur, which means a form of sulfur. It's just there's 8 sulfurs together that make that particular allotrope. All right, let's do this one up here. OCl minus. Now this is a polyatomic ion. It's not going to net 0. It's going to net what? What's going to be the net charge? -1, because the charge of the polyatomic ion is a -1. So who's prioritized here? Oxygen will get a -2. I'm hearing you. Okay. So the -2 plus something equals -1. So chlorine's oxidation state is what? A +1. Give me a 10 if you're doing okay. Give me a 10. Just want to see like approximately where we are. Okay, so we're doing okay. Let's do one more for kicks and giggles. This one, calcium permanganate. Well, I take attendance like a good teacher. Calcium permanganate. So right now we're just assigning oxidation numbers. We're just determining how do we look at a formula and assign an oxidation number to it. So just give me a second, I have to refresh. What do you guys on assigning to calcium? 2 plus and the rest? Or actually, tell me your sequence. You did calcium with a 2 plus first, and then the oxygen with a 2 minus. Okay. So here's what you can do it in 2 different ways. Calcium bonds with this polyatomic ion, right? Okay. So calcium gets its 2 plus. Overall, if I just have permanganate, ignore the 2 out here just for a moment. Overall, if I just have permanganate, what should its polyatomic ion charge equal? What's permanganate's charge? Say again? -1. It is a -1. So all of these oxidation states should equal -1. Okay, so let's do it that way before I start putting it with a constant. You told me oxygen got a -2, so -2 times 4 is -8. -8 plus something equals -1. Plus 7, right? So manganese is a +7 charge, and you know that's okay because we just went over that big chart that had manganese that went from from +2 all the way down to +7. So you're going to find out some numbers get big, like 8, 7, 6, stuff like that. But as you see in here, if you have a +7, and so sorry, the -2 times 4 is a -8, plus 7 would be overall what? So -8 plus 7 is -1, and -1 times 2 is a -2, right? -2 and a +2 equal 0, which is why the whole entire compound itself equals 0. So it works out both ways, whichever way you do it. Okay? Yeah, so we did just the permanganate, so -2 times 4 is -8, plus 7 is a -1, correct? -1 with a 2 on the outside means I have 2 of those, that's a -2. So -2 combined with the calcium, that was a +2, nets to 0 still because the compound as a whole equals 0. Okay, so this is just a practice that we can apply in a reaction situation. So there are actually some reactions that are very, very complex to balance. You know, we've been balancing reactions for a year at this point, maybe 2 years, maybe 5 years, depending on, you know, where we are, from 7th grade to 12th grade. So we've been balancing reactions. Now, we've been dealing with things that are very easy to balance. Sometimes these things are more complex, and we have to include balancing with water, balancing with acids, balancing with bases, and balancing with oxidation states. And so you saw in your alum lab, I walked you through that because it's a very complex reaction. And if you try to balance it by yourself, you'll be kicking yourself because it's a rough time. So we're going to start balancing with oxidation states a bit more today. I already went through this a little bit on your, you know, as a warm-up, but I always use oil rig. I never use Leo says GER. I never learned it, but now I have, so I will say that occasionally. But oxidation states change when oxidation occurs and when reduction occurs, right? Oxidation is loss. Loss of what? Electrons. So if I lose an electron, what happens to my oxidation state? Does it get higher or lower? It gets higher. As I lose negative charges, I get higher in oxidation state. So reduction, as I gain electrons, what happens to my oxidation state? Reduces, right? Reduction is reducing. So that's another way to remember that as well. Also, can these occur by themselves, or do they have to occur together? Pick one. Where do you think these oxidized electrons are going? They're going to go reduce something, right? They're not just like going off the la la land, right? They are going to do a purpose. But ones lost are gained elsewhere. They have to occur simultaneously. Never, never, never will they occur separately. So I just had a couple pictures for you here. So the reducing agent, or the thing that's losing electrons, being oxidized, you can see that here, is giving these electrons down here to something else. I'm going to cut the lights down just a little bit for that. So they have to occur simultaneously. That's an easy multiple choice question to get right on your multiple choice for this later. So, and the new terminology is now coming out for you guys to see. If I am oxidized, my process is loss of electrons, but my name is called the reducing agent. It is opposite, because if I'm the reducing agent, I am the agent that causes reduction. Basically, I am giving, so A is giving B electrons. So what am I doing to B? I'm reducing it. But myself, I'm doing what? I am oxidizing as I reduce somebody else. So that terminology starts to play with your mind a little bit. But remember, if you are oxidized, you are reducing somebody else. So you were termed the reducing agent, and vice versa. If I am being reduced because I am gaining electrons, I took those from somebody, right? I am the oxidizing agent. I made somebody else lose electrons. So the terminology is pretty, you have to stop and think about it, I guess is what I'm saying. Okay? Can I move on? Shake your heads or something? Okay. So let's go ahead and assign oxidation states to these reactions. Identify what's oxidized, identify what's reduced, identify oxidizing and reducing agents. So there's a lot from one reaction you can tell me. So go ahead and write down these for yourself. Write down the oxidation states, and I want us to, we'll track them together, but I want you at least to write down the oxidation states yourself first. So whether you're a note taker or not, you're writing this example down. I swear, I'm getting so many emails today. So what's the oxidation state of sodium? Say again? Is it an ion? It is 0. It's a free element, correct? It is a free element. Do not fool yourself. It's a free element. It's not bonded to anything else, nor is it an ion. Okay, chlorine. 0, free element, correct? All right, now we're in a bonded situation. What's the oxidation state that you prioritize? Group 1, so first one, group 1 gets a +1. Chlorine has to balance it out, right? So +1, and this one gets a -1. Okay, so here's how you track. We're going to think of these as 2 half reactions. 2 half reactions make a whole reaction. Okay, so sodium to sodium. Sodium 0 goes to sodium 1+, or +1. What happened to the oxidation state? So what happened to it? Did it oxidize or reduce? So it lost electrons. Yeah, it went from 0 up the number line, so up to the number line means it lost an electron. So I always put this like this, oil, because it lost 1 electron. Oxidation is lost, it lost 1 electron. This is how you're tracking your electrons as you go. Okay, law of conservation of matter means whatever I lost, I also gained, right? So that's where we have to prove that's true. And here's how we do it. From chlorine to chlorine, what happened? It gained electrons. But how many? Truly, yes, 0 to -1 is 1. And I'm going to put that like this for now. But if we track these and with their coefficients as well, and this is already balanced actually, this one is a balanced 1, but I want to show this to you. We have 2 sodiums forming 2 sodiums. So total, how many electrons were lost? 2, because each sodium lost 1. So the oxidation state's correct. Each sodium lost 1 electron. But overall, there's 2 of them, so there's 2 electrons that were truly lost. Well, where do those 2 electrons go? To the 2 chlorines. So 2 chlorines, each of which have a 0 as an oxidation state, each of which has a -1. There's 2 of those here as well. There's truly 2 electrons that are gained in that example as well. So this one's already balanced, but I would actually make us balance it, and that's what we're going to do in a second. We're going to look at it and look for the differences in electrons lost and gained and balance it ourselves with coefficients. Okay, so who is the oxidizing agent? Chlorine is the oxidizing agent, so I'm going to put OA under here. Because chlorine itself is reduced, it is the oxidizing agent. So who's the reducing agent? Sodium. Did I even look at the products really as for agents? No. The stuff that we call agents are always reactants. So that's another note to make. These are always going to be reactants because they're the things doing the dirty business. They're the ones kind of just accepting accepting or giving away electrons. This is where the action kind of starts. All right, so we could do the same thing for here, but it's very similar, so I'm going to skip that one for now. Let's start balancing one by ourselves, okay? So I call those half reactions, right? Half reactions will also be written like this. You will need to remember how to write them, or at least identify where the electrons are in the half reaction. So go ahead and write down these so I can use this as a teaching example, and I'll do another one with you guys in a little bit. But the 2 half reactions, of course, will sum to the full reaction, but it just isolates a single reduction or a single oxidation. So we already knew that sodium had a 0 and now it has a +1. And we said that was what again? Oxidation or reduction? It lost electrons, right? Where did it lose them? It lost them to chlorine, we know that. But the way the loss is shown, so this one is oxidation. The place the electrons are shown are always in the products. And because we have those 2, like I said, we were balancing with, you can see here. The lost electrons are shown as a product. The gained electrons are always shown as a reactant. So RIG, reactant, I don't know if that's going to be something you memorize or always try to write it out for yourself, but the reduction half reactions always have the electrons as a reactant because they're gaining itself, and then the resulting part has already been reduced. Okie dokie? So that's the main difference in the half reactions. So when I say write a half reaction, I literally mean show me the electrons as well. Okay? Cool? Moving on. So, we just did that. Yeah, we did that. Okay. So go ahead and for this one, write out the half reactions for this one. Half reactions. So I want you to decide if you can tell me first off who is changing. We have how many different elements involved? 3 different elements, but we can only have 1 half reaction for oxidation and 1 half reaction for reduction. So before you write half reactions, I recommend you write down your oxidation states. So let's assign them across the board. Who can you automatically tell me? The oxygen is a what? 0. So oxygen gets a 0 for its oxidation state. Starting over here, who can you automatically tell me? Let's just do sulfur first because lead is a transition metal. Transition metals I always say for last because they're the ones that can have like a variety of oxidation states. Whereas sulfur is just it's a group 6A, right? So what's its state? It's what? 2-. Okay. What's lead? It has to be a 2 plus. And I know my numbers are off, that thing's in the way. I think I can move that. Yeah, okay. So 2 minus and 2 plus. Keep going. What do I know here? Is a 2 minus, and so lead has to be a 2 plus. And then this oxygen is a 2 minus. Oh no, it's not diatomic, it's with sulfur. It's only when it's by itself is it diatomic. But now that's going to be included in our calculation, right? -2 and 2 make -4, so what does sulfur have to be? A 4 plus. Okay, who's actually involved in oxidation reduction? Who's changing oxidation states? Sulfur and oxygen, what's lead doing? Chilling, it's not doing anything. It's not taking electrons, it's not getting electrons. So this is where I want you to write out the half reactions. So sulfur is in PBS, I know. I'm going to write out PBS because it's a solid and I can't take them apart, right? It's a solid. I'm going to put the -2 on top of sulfur. Half reaction wise, it forms what? Where's the S at? It's at SO2. So I'm going to write out this is a complex one. I probably should have started you off here, but I'm going to go ahead and finish. Note this is going to be something called disproportionate, but I'm going to talk about that in a second. So SO2 is where where the S is, and it's a +4. Okay. We know that this is going from -2 to +4. What's happening? Oxidation or reduction? It's losing how many? 6 electrons. Okay. So I'm just going to label this right here as such. You guys said it was oxidation, and there was 6 electrons difference. I might actually wait to balance this one with you guys again later because I started you off really complex. Let's just keep talking about this when we move on. So sulfur to sulfur oxidation. Oxygen, we know, is the other one that's being involved, right? So O2 yielding, where's the O at? Where's it at? In both. That's why I said it's called disproportionate. And both of them, though, they go to a -2, correct? So from 0 to -2, what's happening? It's gaining, so it's being reduced, correct? Okay, I'm going to pause on that one because this is more complex than I need to start you off with because you have oxygens in 2 places. We'll draw half reactions again for another one. This was basically identifying oxidation reduction. All right, so there are, like I said, I'm going to skip that for a second. There are 3 ways to balance reactions via oxidation reduction style. The first one we're going to do today is just really brief, change in oxidation state, and that's what we kind of started with doing the half reactions. But more than anything, it's assigning oxidation states, looking for things oxidized and reduced, and then balancing. And that's it. It's not bad. And so this oxidation state change is also called ion-electron method. We won't see it too often, but I need to expose it to you at least once right now. And then the other 2 we're going to do tomorrow. So we'll do Wednesday. Nope, Thursday. We'll do Thursday. Today's Wednesday? Yes. Okay. So we'll do those tomorrow. They're very easy to do together. But it's going to be something that's related to a lab we'll do later on too. So let's go ahead and just do balancing method called oxidation state balancing. And I'm going to do 1 or 2 big examples, and that's about it. Okay? And I'll tell you specifically what I need you to do from yours. Let's just look through this. We're not going to write this down right now. Let's look. Very first step. Write the formula. Okay, we know how to balance. You have to write formulas first. Duh, you know that. Second, assign oxidation states. That's what we've been doing, right? Okay, third, identify atoms that change oxidation state. We did that with the lead and sulfur, or the oxygen and sulfur one. Look for total changes in oxidation states. So you're looking to see who's oxidized and who's reduced. Make the lost electrons equal to the gain. That's where we start plugging coefficients in. That's where we start to balance, because we have to look at the electrons lost, not the number of atoms at that point in time. The multipliers are going to be used as temporary coefficients until we're pretty certain that's what it should be, but we also have to make sure everything is balanced. Coefficients, meaning mass, and charge, meaning electrons. So we've never had to consider electrons before, and this is where we start to. So I'm going to show you this through an example, and then I'll have you take a picture of this at the end, okay? So through our examples, I'm going to do the big boy, which is this one. Write down this reaction. You're going to need some space. This is on the piece of paper packet I've passed out, but it's tiny. So I really like you guys to have those examples in front of you. Not necessarily write examples out. Here's one. So if you are looking to see where I am, I'm on the B section, this very top corner. After I do one example, usually you guys you're fine. So I want to see if we can do this afterwards. My voice is going too, so we'll see where this goes. Are you guys ready for me? You've got the equation written down. What I said the next step was? Assign oxidation states. Okay, so let's go for it in order of priority, right? So what can I do here first? Write these down with me. Say again.
You have the -2 for the oxygen.
Okay, so we oxygen no gets a -2. What does potassium get? A +1. Can you do that in your head to figure out what manganese is? Say again. So tell me how you did that so quickly. 2 times 4 is -8. +1 is a -7. So what does manganese need? A 7+ to balance it. Okay, so we got a +7 here. Next one, what do you know? What's your priority? Chlorine gets a -1, so what's 10 get? A +2 because it gets the -2 and a +2. Okay, next one, what does hydrogen always get? +1, and chlorine will get a -1. And then manganese 2 chloride, -1 and +2. Okay, next one. -1 for chlorine, +4 for sulfur, or 10, sorry. Potassium chloride. -1 +1, and water. Okay, so a +1 and a -2. My pen is really off, so we're going to work with me here, okay? So, step 1, write the reaction. Done. I've predicted the products for you. Soon we will start predicting our own products. Written out the oxidation states. Next, figure out who's involved in oxidation reduction. Look for changes. Who has changed? I heard what? Manganese. So I'm going to write manganese, and I'm going to branch it over to the other manganese. We'll figure out what that is in a second. And 10, I heard. Just do one on top and one on the bottom so you have some space to write. Okay, so what happened to manganese specifically? It went from 7+ to 2+. It gained 5 electrons. So I'm going to put Rig and then put 5 electrons in here so I remember that. And then what happened to 10? Okay, so oil, good. At least we're on the right track. An oil rig has occurred. How many was lost? 2 to 4. So that's 2 electrons that was lost because that's the difference in oxidation state. So right now our job is to balance the electrons. How do I balance 2 and 5 electrons? What's the multiplier that we apply to both that would make, or to apply to each of them to make it the same electrons lost and gained? 2 and 5, right? If you have a number system and you're like, okay, I've got to make these equal, you basically can multiply them by their opposites, by the other ones, and you can get it equal, right? So I'm going to multiply 2 by 5, correct? So when I multiply this by 5, whatever my branch is touching, that is the coefficient for that compound. 5 applies now to 10 over here, and to the chlorine, and over here. Now, I'm adding the coefficients because I need to balance the electrons first, and then I start balancing atoms at the end. All right, so that 2 times 5, this is going to be 2 and 5 as well, but these 2's now go on the potassium permanganate and the manganese 2 chloride. Okay, so now that I have my electrons balanced, do not touch those coefficients, okay? The electrons have been balanced. We're halfway there. Does that make sense? So those coefficients do not get touched unless we absolutely have to. Then we have to refinagle that. Now, I'm going to change my color so that you know I'm doing something different. Now, I'm done balancing charge. I need to balance atoms. Step by step, let's walk through this. How many potassiums do I have? 2. How many do I have on that side? 1. What do I need to do? When I add this 2 over here, am I changing my charge, my electron balance? No, because this potassium and chlorine weren't even involved in redox, right? Who cares what I put a coefficient for there? I'm balancing atoms now. The charge has already been handled. Does that make sense with the difference between these types of coefficients? Or balancing acts, okay. So potassium is balanced for manganate, 2 and 2, we're good. Oxygen, I see it here as a what? 8 over there. 1, so what do I need to put over here? 8, and let's kind of see where that brings us. There's an 8, okay. Now I've got how many hydrogens? 16. What do I have over here? 1, so what do I need? And don't be scared of big numbers. You're like, I don't know if that's right. 16. Okay. 16 HCl. So now I've got a coefficient on everything. I need to double check my chlorines are right, because I know I just added some chlorines over here. How many chlorines total over here? 26. 5 times 2 plus 16, 26. How many chlorines over here? 26. Okay. 2 times 4. So 2 times 2 is 4. Plus 20 is 24. Plus 2 is 26. Score. We never had to change the coefficients of our pre-balanced electrons, correct? We're good. This is basically balancing mass and charge, or atoms and electrons. That's what we're doing here. That's why it's different than what we did before. Okay? Let me tell you 2 that I want you to do. Let me look on your sheet. Because once you know how to do this, we don't need to kill a dead horse, right? So I'm going to have you guys do, I already picked out some. Let's do, go ahead and circle 1. And this is under the part B, called Balancing Redox by Change in Oxidation State, little problem set. You're doing 1. And 6. Go ahead and start with 1 and 6 right now. I'll tell you what else I need. And now I'm going to double check that. So right now I have 1 and 6 in the little first section. That was called 1 through 10. And right now I'll put 6 and 7 on the more practice, but before you circle these, I'll make sure I actually do it. Now let's just do 1, 3, 6, and 10. So here's what we're going to do. You're going to start to assign 1, 1, 3, 6, and 10. Yeah, 1, 3, 6, and 10. So you have 4. You're doing 4 of them, okay? And then in terms of homework, look at the global chemistry crisis, which is the ocean assignment. And look, and I want you to start researching a topic that relates to chemistry that we've done in class, or kind of starting right now with redox, or maybe something you know that already relates to chemistry, and like oceans, climate change, chemicals that relate to the atmosphere and the water, because you took apes and you know a little more about that. So I want you to start researching something about that. I'm not giving you any specific guidelines, but I want you to choose something so that you can add to the table what you have started. Show me that you've started, and I'm happy. Okay? So you guys have about 7 minutes. You probably can knock out 2 of these. Let me know if you need some help. Yeah. I'll leave this up here if you would like to take a picture. I feel like it's very detailed. It will hold your hand as you go, but it's also wordy, and you probably can dumb that down to like a 4-word process. You know, oxidation states, look for change, electrons equal electrons with coefficients, and then balance, like true balance. So I'm leaving that there for you, but you know that you can go with your process as well, because I think it's working.